everybody. My name is Ray O'Mahony and I'm joined by my colleague Tarun.
Hi there.
This morning we'd like to welcome you to our second webinar, our second scheduled webinar. And this morning's webinar we're probably going to discuss and demonstrate the capabilities of Nastran and Nastran simulation tools within your collection. So as you can see on the screen here, there is a number of products as part of the product design and manufacturing collection. And it's great that we have all this capability, and now we can add additional capabilities to what we already have with Inventor FDA. So again this morning, again as I just said, you're joined by myself, Ray O'Mahony, Technical Manager and MFG Specialist, along with Tarun, who's a Tech Engineer and Simulation Specialist. So with that in mind, Tarun's going to very much go through Nastran and its capabilities and why Nastran-in-CAD, and ask those questions. What is Nastran-in-CAD and its functionality? So again, these are topics that we're going to cover this morning. And the big thing for me personally is, as an Inventor user for many years now at this point, the difference and the additional capabilities we have versus from Inventor FA through to Fusion 360, and that's in Nastran-in-CAD. Tarun will go through some live demonstration cases and some live examples, and we're going to discuss in more detail topics such as linear static, which is very much based inside an Inventor, the constraints of linear static, and then obviously versus non-linear static analysis. We're going to go through an example of linear buckling, and then some frame analysis, and again some quick tips that we've gained over the last number of months using Nastran. So the big thing about Nastran is, and the thing that I like about Nastran is upfront simulation very quickly and easily, and an integrated solution. And one of the main things about Nastran really is, as you can see here, we don't have to physically model things to apply to run a simulation. We can do things like bolted connections, so we can actually simulate rather than drawing in the bolted connection. We can put in constraints that include that bolted connection geometry already.
Basically, we can simplify the complex geometry, can take out the bolts from the model and use the Nastran simulation bolts for the assembly purposes.
So again, we can reduce modeling time and benefits in the simulation being quicker if we use that method rather than actually physically design those bolted connections in assembly. Yes. Then obviously we can move on to time and transient dynamic load. So for example, we're talking about movement of assemblies, we're talking about simulations at certain points along that motion. We can talk about vibration, which is really like modal analysis in Inventor, but a more extended functionality of that. Yeah. And the big thing for me is fatigue and shock analysis and impact analysis with Nastran. So that's huge in my mind, because with Inventor FEA, we are limited to linear static, which is great. It has its purpose, it's great for upfront simulation. We've got mode analysis. We can do dynamic stressing, dynamic loads using the dynamic simulation environment. But Nastran brings that to another level. And I suppose this morning we just want to make you aware of what you can do within Nastran, how easy it is to do it in Nastran, and how tightly integrated it is with your Inventor model. Another example of this is obviously the temperature. So again, we don't have this functionality in standard Inventor FEA. What we do have is within temperature we can consider the effects of temperature across components, convection, conduction, that kind of thing. Yeah. We can solve for temperatures. Again, we can pre-stress and put in thermal stresses on particular parts. Exactly. And there's some good examples we can show you. Now, we're not going to be able to show every example today in the time that we have, but this is just to give you a bit of a taste. And the big thing for me, and this is the huge part for me with Nastran, is to extend our FEA analysis to have the ability to do nonlinear analysis. Past the point of the elastic limit of that material, or we're not defined by the constraints of the material any further, we can go beyond that point, that elastic limit, to see how the actual part would react or how it would fail in future. Yes. So the common objectives, as I just pointed out, we have, remember, PAY, ATTM, which is basically assembly with movement, time, temperature, and nonlinear. These are the key areas that we focus on Nastran, and the key differentiators between what's an Inventor FEA and Nastran plus Fusion 360. Just for those of you that aren't aware of Fusion 360 as part of your collection, it is a very good design tool that can be used with your Inventor workflow and your simulation workflows where you can do first pass simulations, you can do first pass designs, you can include those designs in Inventor assembly work and moving forward. It's something that you should look at in time to come. You have it part of your collection. It is a very powerful tool, and it has its strengths in the fact in the manufacturing area where in future we'll be talking about one-touch manufacturing system where you will have all your inbuilt capabilities as well, which will be discussed in our next webinar series. So we probably get, when we talk to customers quite a lot, we do get questions like, well, we already use ANSYS. Now ANSYS is a very, very powerful tool and has been in the industry quite a long time, and it would be kind of an industry standard for all FDA experts out there. But the idea of Nastran really is to kind of, you know, your engineers in the office, they don't have to be simulation experts to use Nastran. It's like giving a first pass to those particular simulations before you may include the FDA expert in time to kind of, I suppose, confirm your results or maybe help you tweak the particular design in order to achieve a better result downstream. Yeah. So I think Nastran is a very good tool for the likes of me, who's been, and Tarun, that has been using Inventor extensively, that we can do a first pass in FDA. I also might add that Tarun here has used ANSYS and other simulation packages, and obviously has used CFD as well quite well. So from his own experience using Nastran, he thinks it's quite a capable tool. Do you agree?
Yeah, definitely.
And we think that it's good for the likes of me, who may not be a simulation expert, but are willing to dabble their feet in it, do a first pass, and kind of get to the grasp of what we're doing in a non-linear environment.
Like, I'm not saying that Nastran can do whatever ANSYS can do, or like, even if Nastran is not that powerful as ANSYS, but ANSYS is really, really costly. And in today's world, I think all companies need to be cost effective.
Yeah.
And to be cost effective, Nastran is the best tool that you can use. And I have compared few results of Nastran with ANSYS results, and they are very, very comparable.
Yeah.
So there is no point in you throwing away a lot of money for ANSYS instead of Nastran.
Yeah.
So yeah, I'll go for Nastran with the beginning, and then as the problem gets complex, then I'll look into other softwares if needed.
Okay. And again, you're getting Nastran itself being part of the collection suite now, as people are on this call, subscribers to the software, have this capabilities already.
Yeah.
So they're already available to you. You can download and install Nastran at any particular point and get it implemented and up and running in no time at all. Very much like what you do with an Inventor installation. It's a tightly integrated solution within Inventor, so it's going to be seen as a tab within the Inventor environment. So you're not importing or exporting and importing into other software.
Yeah. It's
directly built in. So any design iterations that you may have or changes, they will automatically come across, and your loading constraints remain the same. So I said, I think we can justify the cost. Of course we can justify the cost. If you're a subscriber, you already have this tool. So there's no additional cost to you. You're paying your subscription benefits. So you have this tool. So of course we can justify the cost. Why would you include FDA in your workflow? For the very example is to test and work on digital prototypes and rather than produce physical prototypes.
Save time.
And save time, save costs, save manufacturing costs, etc. So again, it's a good verification, validation tool of your design.
Yeah.
And again, it reduces the impact of creating physical prototypes to kind of capture intent and so forth like that. So again, Nastran allows you that capabilities where you can extend capabilities such as fatigue analysis, buckling analysis,
shock, vibration, heat,
everything. So again, at this point you can see, and this is just a summary of what we really do. So all this Nastran-in-CAD software, a general purpose finite element analysis tool embedded in your CAD system, which I just pointed out. It's using the Nastran solver. The Nastran solver will be common across all the Autodesk platforms on the manufacturing space. A tool that eliminates physical testing. There is, however, I tend to disagree with that statement sometimes, because there is times where you may create a physical prototype to just validate the results for testing. So
it's necessary to do a physical testing because softwares are not a real, in real life things are different. So in software it's all formulas. So it never take out the physical testing. The thing is, the number of physical testing you are doing for a prototype, that can be reduced using the software.
Yeah.
And that's our target. That's the target. We do not replace the physical testing. We reduce the number of physical testing and go for the accuracy or the accurate physical testing in a one go or in two goes. Like before, I've been working with one company and they have done loads of physical testing, 10 or 12. But the company who was using FDA, they did only 3 or 4 testing. So they saved a lot of time and a lot of money. So that's what it's aimed for. Nastran, that's the aim for Nastran, not to eliminate physical testing, but to reduce the amount of time we do physical testing.
So again, that brings us on to the point, again, to reduce the amount of physical testing, reduce costs. Who cares? Directors of engineering managers, to meet project deadlines and so forth like that. So we can capture maybe issues earlier on the project phase than one or too late, where we may have to remanufacture things again. So I've done my bit of talking at this point. I think I'm going to pass it over to Tarun. And Tarun's probably going to go through the topics that are on this PowerPoint, and he's going to give an explanation on what each is and what the capabilities of Nastran, and go through some live examples. So Tarun, please go ahead.
Hi guys, so I'll tell you about some of the functionality in Nastran. So we'll start with linear statics. Stress, strain, and deformation are applied using loads and constraints. And stress, strain for a linear static analysis, the graph of stress strain is almost a straight line. So and it goes up to the elastic limit. So that's where linear static analysis ends. But the thing is, then comes the nonlinear static analysis, which extends that graph up till the fatigue limit. That is, we capture the plastic region, we capture the fatigue region, and it gives us all of the complete analysis of a part. Then going on to buckling. Buckling is also included in Nastran. Then the normal modes, pre-stress static and normal modes. The heat transfer that we can do in Nastran, we can assemble composites, the plies, where the laminates are overlapped each other, and the laminates are in different directions. So we can create a composite and analyze the stress and strain in that. Then assembly modeling, we can do all kind of movements and contact, like separation, bonded, welded, offset bonded, and then screws, bolts. So we can do all kind of contact modeling, surface to surface, edge to surface, frictionless contact, friction contact. So we can almost do everything in an assembly that can happen. We can even penetrate one object into another using master and slave surfaces. So moving on to thermal stresses, then non-transient heat transfer, nonlinear steady state heat transfer, random response, frequency response, linear and nonlinear transient response, advanced nonlinear and hyperelastic materials. I've been working with few hyperelastic materials, and it gives me a good response about hyperelastic materials, and it shows me that it can be done in Nastran. So yeah, hyperelastic materials are valid to do in Nastran. Impact analysis and drop test. So these were the functionalities in FEA in Nastran, and I would like to now tell you about the different analysis FEA softwares in Inventor, Fusion, and what is Nastran. So in Inventor, we have two stress analysis FEA programs. One is inbuilt in Inventor, and one is Nastran. So what's the difference between both of them? In Inventor stress analysis, we only have associative CAD geometry, we have linear static stress, and we have modal analysis. We have only these 4 functionalities. But in Nastran-in-CAD, we have all of these functionalities, which is a major plus for FEA solver. Well, to tell you about Nastran, Nastran has a good bit of history, it was developed in 1960, and since then Autodesk has bought it in 1990, and then they have developed their Nastran software themselves, which is working really well this date. So yeah, these are all the capabilities of Inventor FEA, and these are all the capabilities of Nastran. And one more thing, that in Fusion 360, the FEA solver is the same as Nastran-in-CAD. So Nastran is induced in Fusion 360. So if you are doing anything in Nastran in Inventor, you'll get the same results in Fusion 360. If you use the same settings, you use the same loads and constraints, you'll get the similar results in both Inventor Nastran and Fusion 360. So that's about Inventor versus Nastran.
So there's one other thing that we forgot to mention there is about the hydrostatic analysis.
Oh yes, I'm really sorry. We have also added, Autodesk have also added the hydrostatic loads, which allows us to directly apply pressure loads inside a wall of a tank or something like that, which was not available earlier. It has been introduced in Nastran 2020, and I'll be going to use in one of my simulations and show you how it's done. Now, coming to the FEA process and how it's done, what's like, if you want to say in layman terms, what is a FEA process and how it can be designed. So first you create the geometry, that is like you use any 3D softwares, SolidWorks or Inventor or anything. You create the geometry. Then you can assign the properties in the 3D software itself, or you can bring the 3D geometry into a FEA solver. So from creating a geometry, bringing into a Nastran solver or any FEA solver, then you assign the material properties, then you create a mesh, you apply your constraints and loads, and then you analyze the results. So all these steps are integrated in Inventor. That's the best part about Nastran. And it just takes one click to switch from Inventor to Inventor Nastran. So that's the best part. Instead going on to importing your model into some other software just for analysis, that's the good thing about Inventor, that you don't have to do that. You just need to go to the Nastran, do the analysis, you analyze your results. If you need to change your geometry, you can switch back to Inventor. You can change your 3D geometry in like seconds, and then come back to the analysis part, remesh it, and do the analysis again, and see if you get your results or not. So it's that easy to do this in Inventor Nastran combined. Moving on, now I'll start with the live demo and show you some of the capabilities of Nastran and what it can do. So there are three major topics we are going to cover today. One is I want to show you guys the new hydrostatic loads, but I'll show you that with the linear versus non-linear static analysis. I want to compare the results, and I want to show you guys what's the difference between linear and non-linear static results when we use the same loading conditions and same constraints. Okay, and I'll show you the results using hydrostatic loads because it's a new feature and I want to introduce it to you. So I'm going to start now, and let me switch back to my Inventor part. Yeah. So yeah, moving on. So this is a quarter geometry of a tank. So just think of it like there's a symmetry condition over here and a symmetry condition on this side. So it's a complete tank in a 360 model, but this is only a 90 degrees just for symmetry purposes and to make the model or the computational time less. So this is geometry, and now we'll move on to, okay, this is the way. Okay, we'll now move on to our Nastran part. The material being used is stainless steel. So moving to Nastran, this is the Nastran ribbon, and generally the flow of the simulation and how we develop the flow is from left to right. So we start from making materials, assigning material properties, Then we go on to idealization, where we define our element type and the material to the part. There's connectors which can be used to simplify your geometry or your simulation. Then there are constraints, then your loads, then you can make your contacts, then you mesh, and finally you run and you can load your results. So see, it's that easy in Nastran because all the workflow is from left to right. You start from the left, you go to the right, and that's everything you have done. So that's about the workflow. And now moving on, I'll start doing the simulation. So to start with it, I'll just remove everything. It's all as new. Now, the first step, I already have the material with me. So my materials is in here. I don't want to import it. It already reads the material from your CAD geometry. I'll start idealizing my elements. So I'll use a shell element for my model with a 2.5 mm thickness and the associated geometry. If I don't take this, it will take all of the model and assign the same property to it. If I take associated geometry and select faces like this, it will assign only to those faces. So yeah, I want to assign it to all of my body, so I'll leave it like that. And now, why shell elements? What are the difference between solid elements and shell elements? So in Nastran, to make things easier, solid elements are applied to thick bodies or which have considerably good thickness. So over here we can see that we have thickness of 2.5 mm and my geometry's height is about 2500 mm. So when the thickness is not as comparable to the length and width, then we always use shell elements because it's easier for the Nastran solver to compute it. In shell elements, we make 2D elements. In solid, we make 3D elements, and in line, we make 1D elements. So we have 3 types of elements: solid, shell, and line. That's how it works. In shell, we have to define the thickness, and it creates a surface for me to calculate all of the results. So that's first part. We have assigned the element type. Now moving on, we define the constraints. So yeah, as I told you, we need to define the symmetry constraints on the faces over here. So first face, symmetry, X symmetry from here. Then moving on to the next one, we have this Z constraint over here. So Z constraint to this face. You can see it's in the Z direction, so I have to do the Z constraint, Z symmetry. Okay, so using these two symmetry conditions, I have actually made the quarter of my geometry into a 360 part. And now constraining my base so that it doesn't move in any direction. I want to constrain my base, but just in only one direction. That is, I don't want it to translate in the y direction, so I'll fix it over there.
So just to add to that, before you exit the box, you can see that there's a number of constraints that you've applied. There's TX, TY through to TZ.
Yeah.
You also have RX, RY, and RZ. So just to explain what those are, there's basically degrees of freedom. So people that have been using Inventor will understand what I mean by degrees of freedom. A part's got the flexibility in all axis or movement in all axis. So what we're doing is we're able to constrain on a particular axis and apply that constraint as well. So
definitely. Yeah. That's a good point to note. Like, these are all the 6 degrees of freedom. So translation TX, TY, TZ, and rotational RX, RY, and RZ. Okay, so we can choose these according to our need. Okay, I'll cancel this. Also, I just forgot to mention this red part that you are able to see over here. So this is a full tank, but the red mark. This red area shows how much water level is in the tank. So this is the top water level of this tank. Okay. Now moving on to the loads. I'll do the loads now, and I want to use. These are all the types of loads we can apply. Force, moment, distributed load. Now this one is new, hydrostatic load. We are going to use this. Previously we used pressure, and then we used to apply variable load definition to do the hydrostatic load. But no, we don't have to do that anymore. We can apply gravity, rotational force. So all kind of forces are available for us. So we are going to use hydrostatic load. And how this works is simple. So first you can split your body till the level where water is filled up. So I've split my faces, inner faces, till the level where my water level is, and then I can apply the hydrostatic load on it. So it is asking me to a point on a fluid surface. So this is the top level is the fluid surface. I can give them the point on a fluid surface. I've given them the point. Then the fluid depth direction. That's the fluid depth direction in the along the y-axis. The fluid density, we are taking water over here, and the surface pressure. The surface pressure is the pressure on the top of the surface of the water. Over here, we are taking the surface pressure as 0.001962. Okay, and but I don't have the faces selected. I'll have this one. I'll clear it. This, and this. Okay. Well, you guys can't see the arrows yet, but we will soon see it. Sorry. See, you can adjust the arrows, and there we go. All our hydrostatic loads are applied to it, and we are good to go, I think. Yeah. Okay, and we don't have to do any variable load conditions in here. It's just simply you choose the top surface, the top one point on the fluid surface, then you specify your surface pressure. Actually, it works like this. So this is the pressure on the top of the surface, and then you calculate. Sorry, I just wanted to show you this. Sorry. Second. Where is it going? There we go. Yeah. So that's how you calculate the pressure at the bottom of the tank. So your top surface pressure plus the hydrostatic pressure that you apply. So that's how it works. And my surface pressure over here is 0.001962. My fluid density is this. My direction of the fluid is this. And my point on the surface of the water is this. Okay. Now we're going to check this. Now we need to make the mesh. My mesh I'll take as a 75 mm mesh. Okay. And remember, we are doing the linear static analysis only right now. Okay.
So just to explain what mesh is for people that may not understand, a mesh is very much like a grid. It could be made up of squares, triangles, or just linear geometry. It all depends on the model that you're simulating in. So it's just basically, if you imagine that you see those little rectangular boxes or square boxes on the model, there is a number of nodes within those particular boxes that will give us our simulation points and give us our results back. So the more detailed mesh you have, the more accurate result you have. It all depending on the application.
Well, you have to make you have to make, either you can have a good mesh and get accurate, very accurate results. But that will take a lot of time. Or what you can do is you can reduce the mesh size and start by inaccurate results. And as you go on, you can see how much result is improving by refining the mesh every time.
Correct.
And if it's not changing much, you can stop refining the mesh at that moment because the results are already accurate and it won't be accurate any further. So yeah, there is a mesh convergence thing that you need to do before you run the model. Okay, so I think I'm good to run the model.
We should have run the model while we're talking.
Oh yeah, sorry about that. I'll just recheck once my loads. Yeah, this seems good. Okay, looks good to me. We run the model. Won't take long. Just a few seconds. Yeah. Also, while we are waiting for the model to run, which won't take long, yeah, so it's almost done. Sorry. Okay, I'll show you the results. So this is what I got from my simulation. We'll compare the displacements of the corner nodes in our simulation. So it shows me 18 mm is the maximum deformation that I'm getting using linear static analysis. And you can see how it's being deformed. Just have a good look. And that's the result I'm getting using linear model. Now, what I'll do is I'll duplicate my model. So that's easy, like you can save your linear model and then you just go duplicate your linear model, go to edit, change these 30 types. These are all these 30 types available over here, from linear static, non-most, linear buckling, pre-static, non-linear static, non-linear buckling, and everything, all the fatigue and vibration fatigue. So we are going to do the non-linear static, and with the non-linear static one, if we come over here and go to options, we can see this one, this option, large displacements, that is switched on now. In linear static analysis, we don't have that option, but with the non-linear one, it's on. So it means that now large displacements will be captured and the results will be calculated according to that. Okay, we switch on the linear and we don't make any other changes, we just go and run the simulation again.
I have to stress this point here that what Tarun is doing is, again, we have a model that's generated using a 3D model. We can import, we can use any CAD functionality to import different types of models to be included in our simulation, such as SolidWorks Pro Engineer, that kind of components as well.
Yeah.
But I can't stress enough how easy this is. So we can do multiple simulations, or copy the simulations within the model browser.
Exactly.
Apply different simulation types.
We don't have to rework again the same thing. We can just copy and change few of the parameters and go for it again.
Yeah, so we can do a lot of work up front,
Yeah, exactly.
and then we take multiple copies of that simulation and get the simulation results. So it gives us a number of iterations that we can work with.
Now, looking at the nonlinear displacements. So, do you remember the value from linear static stress analysis? That was 18.04, and now it's showing with the nonlinear one, it's showing me actually that this deflection is much less. That is 11.81 m. So that's something about the accuracy of the result. So it almost changed by 60% or like 30%. So definitely going for nonlinear analysis is a benefit, but what I'm saying is the workflow should be first performing the linear analysis, verifying your constraints and loads, and then going for a nonlinear analysis, because it's easier for Nastran to verify your loads and constraints while solving it in a linear static analysis rather than in a nonlinear one, because nonlinear are a complex solutions. So we need to verify all our constraints and loads and make sure that they have been applied right, and then we can go on to nonlinear one and run the analysis again. So that's about the nonlinear and linear analysis, and now I'll move on to linear buckling. Okay, this is the result. Finishing Nastran. Just a minute. I'll close the model, check the changes. Now moving on to buckling. Okay, so what is buckling? Buckling is a failure mode quite commonly experienced for mechanical components and structures. Linear buckling is also called eigenvalue buckling or Euler buckling analysis. I'll tell you why it is when I analyze the results. I'll tell you why this name. And it predicts the theoretical buckling strength. So basically what a buckling model in Nastran is, it calculates the eigenvalues and the buckling modes for you. I'll show you in a minute. So just straight away, this is the model, and we'll straight away move on to Nastran. While working in Nastran, I'll show you and I'll take you through a few of the things. So first step, we go and change our analysis to linear buckling, and then there are options, and we go to modes. So what are these modes actually? Why are we changing modes? So these modes, the number of modes that it's calculating, these are the failure modes basically. So it tells us there that how many failure modes will this model have when we apply linear buckling to it. So, but practically, if we see, the first failure mode is the most important, because that's where you'll decide what load you want to, what loads, what is the minimum load you want the part to handle. So the first, basically the practicality of linear buckling is the first failure mode. So we'll look at the modes in a while. So now setting up my model, open a part, go to Nastran. Okay, so now we'll idealize our elements. In this one, we'll choose a solid element. Now, how to choose a solid, a shell, or a line element? So always for thin elements or sheet metal parts, go for shell elements always. If the parts are thin, always go for shell elements because it's necessary to have, for a solid, it's necessary to have some nodes or meshes on your thickness. So for a thin part, if the mesher is unable to make few of the meshes in your thickness, or if there's only one single node in your thickness, then it won't calculate, you won't get your results accurate on your thickness. The results won't be comparable to the solid elements. So over here we are going to take the solid elements and the associated geometry will be all of it. So I'll leave it, the material will be mild steel and leave it like that. Then we come on to the constraints, but before constraints we need to go to the connectors. So connectors are something which make our life easier for analysis. So like we have rod connector, cable, spring, rigid body and bolt connectors. In bolt connectors you can simply make bolts for your holes. You can remove the bolts from the content center or wherever you have used for, and you can use bolts from Nastran, which is already designed to do the simulation.
Yeah, this goes back to the point we made earlier about that we can simplify the simulation by reducing both the connections. We don't need that information. We can predetermine that by using the Nastran connectors here. And Tarun's about to show you how we're going to simulate where this component, as you can see, it pivots along its back there, and there's a shaft. So that's why he's going to use this connector option here now.
Yeah. So what I'm going to use, we don't have much time to explain all of the connectors. We are just going to use the rigid body connector and show how it's done. So a rigid body connector on the back, and I want the point at the center. I will choose this face, I choose this face, and that's how it's done. So I've connected both the faces to a single center point over there, and these two points are connected over here to this point. And I'll do it okay. And now what I can do is I can just simply, to constrain those two holes, I can constrain this point. So I'll constrain this point as fixed. Yes, and that's it. My constraint is done. It's that easy, and I don't have to use multiple connectors to do that.
Right.
So and now we're going to use the load. We're going to define the load. The loads are So I'll define a load of -1. I'll tell you why in a bit, and it should be normal to the surface, and the surface will be this. So I'm loading this with a magnitude of -1. Okay, moving on. Why use the -1 load? I'll explain it to you in a while, because in linear buckling we calculate the eigenvalues, and I'll tell you in a while what are eigenvalues. Okay, now I think we are good to have our mesh. Everything is done. Yeah, 10 is my mesh. I'll generate the mesh. Okay, we need to understand what are contacts also.
Okay.
Yeah. So over here we use the automatic contacts. I'll explain you the contacts in a while in the next simulation. And now we can run the simulation. Good to go.
So as we're running the simulation, you can see that it may take a while, and this one, I mean, this is a linear one, we're going to
take much long. Yeah.
So you can see very quickly, especially how we put in the connector at the end, how quickly we can constrain or fix multiple geometry without too much of an effort.
Yes.
In standard Inventor FDA, I would have to go into each one of those surfaces and fix those.
Select it manually and do everything manually.
Or in an extreme case, if I wanted a really accurate result, I would have to include the shaft, then put in the context for the shaft, fix the model against the shaft, etc. So there is a time-saving element to all this. So you can see very quickly we can do, as I said, bolt connection, shaft, rods, all that kind of stuff can be done and preempted on the model. So we're simplifying the simulation very quickly and easily. And again, we get an accurate result because we have a very good representation of what we're trying to achieve.
Basically, that's where the connectors are beneficial, because you don't have to model parts, you don't have to mesh them, you don't have to generate contacts with them. They are just available to you and you can use them directly.
Yes.
Instead of using a part and meshing them. That just generates more computation time. So that's not good. Okay, I think our simulation is done. Yeah.
So we're just waiting for it to generate preview. So I think Tarun's going to go discuss this about the system requirements, but I think what we'll do is we'll just focus on this for a minute, and then we'll go to the main book, we can discuss that.
So over here, now these are the 5 modes it has calculated for me, and the first mode, you can see the eigenvalue is 13875. So 13,875, that's the first failure mode that I'm having. I'll show you in a bit. So what does this mean? Whenever the eigenvalues are supposed to be the load factor, so it's telling me that it will fail, the model will fail, or the first initial buckling will occur at this load factor into the load that I applied, that is -1. So any load you apply, it will generate you this load factor, and then you multiply this with your load, and you will get the first failure buckling load, basically. So this multiplied by -1 is my first failure buckling load. So that's how eigenvalues work over here. And these are the 5 loads. But I already said that first one is the most practical one. And let's suppose there's a company who wants to design this component not to fail under 20 kilonewtons. Okay, so now this definitely says it has failed. Then what do we do? So we finish off in Nastran, we have seen it's failing. We go back to our part, we change our part, we do some, like I have done it already. So, but what we do, we change, made some modifications. We include some new materials, new areas, and some extrusion just to make increase the strength of the part. Then go back to Nastran. Just see how simple is it. I go back to my 3D model. I make some design changes. I come back to my Nastran interface, and I just regenerate the mesh again. That's all I have to do to include the new features that I've added. And I go back again and I'll run the simulation and get the results and see if it's okay. Otherwise, I'll go back again and change my model, make some more new features to increase the strength. So yeah, my mesh is complete. I'm good to run now, and we'll see in a minute how it acts. Okay, so I was telling, while it's running, I'm gonna tell you something about contacts. Okay, so we'll come over here. So there are 3 types of contacts available: automatic, manual, and solver. So automatic, how does automatic contact work? So while we were defining our simulation type, if you come over here and see over there in options, we have contact data and contact type. So whatever contact type you define over here, and then if you go for automatic contacts, the automatic contacts will be of this type. So if I make separation contacts over here, or bonded contacts, or sliding or no sliding, whatever contact type I choose over here, that will be used for automatic contacts. Okay, that's the first point. Now, that's almost everything about my automatic contacts. Now, manual contacts. Okay, we won't open. So now there comes manual contacts and solver contacts. So generally, solver contacts, they are created while the solver is solving, and you just define the region of your contacts and everything. But okay, I'll come back to it in a minute. As you can see, our simulation is complete. We are running a bit short in time, so just need to hurry a bit. Okay, now, yeah. Now watching our undeformed edges. Okay. Now my first eigenvalue is 27992, almost 28,000. So you see how much difference this thing made, and my new eigenvalue is 28,000 now. So that's how easy it is, and it definitely won't fail me under 20 kilonewtons. So this model is good to go, and the company would approve it now, I think so, do some physical testing or whatever. But that's how linear buckling is done, and that's how the workflow of linear buckling should be. Also, there is non-linear buckling available in it, but that's now how the workflow is. First you do the linear buckling. If you are satisfied with the buckling load, then at this point I should go to the linear static stress analysis, see where the stresses are, analyze it, and if I think something is missing or there is something fishy, I can just go on to nonlinear buckling and do it. But it's really the end part where we go to the nonlinear part. Okay, so I'll finish off it over here, and we'll move on to a third simulation, which is the frame analysis, and we'll do that in a bit.
So just to continue on while Tarun's getting the model ready, Tarun mentioned about contacts, right? And I can take that conversation while Tarun's getting set up here. So contacts are basically how components are treated within a simulation environment. Are they welded, which is bonded? So I think they're welded to each other. There's no movement. There's no sliding movement.
Yeah.
Is there sliding with separation?
Yeah.
So for example, we could have sliding with separation, sliding with no separation. So sliding with no separation could be a bolted connection, for example, where there's a washer against a plate, and you might have sliding no separation, where it's allowed to slide on the surface, but it will never separate from the surface.
Yeah.
You could have sliding with separation, so you could have that washer loose. So for example, it could slide and it could separate also at the same time. So it's contacts are critical in your simulation studies. If your contacts are not set up correctly, you're not going to have an accurate result. You're not going to get the true behavior of a design in an FAA environment.
Definitely.
So as a big part of your workflow, contacts are huge. Not only your constraints, not only your loading, but contacts will have to be looked at.
Yep.
And there's certain criteria we can do and work on to get that. And certain you can do automatic contacts, we'll make assumptions. It's possibly not the ideal workflow. I prefer to use manual contacts.
Definitely. Yeah.
Again, it may cause a bit more work up front, but at the same time you get more true representation.
Accurate results, that's about it. Okay, now moving on to our third simulation. It's a frame analysis, and I would like to show you the master. Okay, this is the frame on which few bodies are kept and like machines are kept, and we want to see when these are working. Will the load on these will deform the table, or will the failure of the bench occur or not? So moving on to a simulation part. So we'll simulate these tables and the bars. So these are bars and beams created from the frame analysis or frame generator in Inventor. So you'll see what the power of frame generator is in Nastran. Nastran already has that information about frame generator. So I'll show you what it does. Yeah. Yep. Okay, I have my model over here, and now before idealizing, so now there's a feature in Nastran. We are going to do a linear static stress analysis. There's a feature in Nastran that is structural members. So if you see these structural members, right now they are defined as solids, but we want to treat them as a line element. So what we do, we take it all to beams, we define them as beams, and they will convert to a line element. One second. There we go. Yeah. Okay. So we have our line elements for our beams now. Why is it? I'll tell you in a minute. And how is it? I'll tell you that. So, okay. When you come to an idealization, I've converted my beam into a line element, and this is a bar element. So, with the line elements, we have three types of element types. So we have bar type, we have beam type, and we have a pipe type. In all three of them, we can have this input information, which is very critical. Someone was asking me, can we take the cross section of the beam or the pipe into account for the analysis? So that's the answer. Yes, we can. If you go into cross section area, and if you open this, you can define the cross section definition over here, and you can simply, all the information will be calculated while solving. It will be taken into account. So yes, it can be. Right now we don't need this. I'll take it as a structural member. Moving on, I need to idealize my plates on the top, so I will idealize them as solid elements over there. Associated geometry are these, and these. Again, mild steel. Okay, my idealizations are complete now. I would move on to now constraints. So I'm constraining the base of my table. So I'll keep them as fixed. Yep. I'm going to use loads. I'm going to create two loads. One is gravity into -9810.
And just for those people that are on the webinar, the minus values also indicate the direction along the Z.
Exactly.
So the minus is going to go obviously in the negative. So you can see by the arrow indicating towards the bottom of the right-hand screen where G is the arrow pointing.
The next load will be on the top faces of my body, and that will be minus, again, in the bottom direction, 5,000 Newton. Yeah, that's it. I need to create a mesh now. I'll create a mesh, 30. And now the main part is just defining the contacts. Now I'll show you how contacts are done using this example. A few bits to contacts. Contacts is I would say, the most important and critical feature in Nastran. If you get the contacts right, you'll get your solution right. So I have my mesh created. Now I just need to have contacts between the beams and the top plates. So I'll go for manual contacts, and this is the surface contact toolbar. So we have two types of contacts, surface to surface and edge to surface. We can't use surface to surface because our beams are like an edge. So we'll go for edge to surface. And then the contact types are same as before, bonded, separation, as Ray told you before. We have all the types of contact bonding over here, but we'll go for offset bonded. What is offset bonded? So just suppose if we have this beam and it is not directly connected to the top face, so there is some distance between them. So I can specify a maximum activation distance of whatever the distance is, or more than this distance, and then it will act, both of the features will act as bonded. So that's what offset bonding is. So we'll use offset bonded, but the surfaces. Now master and slave, where it is used and how it is used. Master and slave entities are generally used for penetration, where parts are going into each other. So if I say this top plate collides with this beam and they are merging, or one is penetrating into another. So whatever surface is penetrating into other surface, the surface which is being penetrated will be taken as slave, and the surface which is penetrating should be taken as master. So in Nastran makes your life easier. So when I go to surface, edge to surface, when I go to separation, I want to show you this, 1 second. Okay, so see this penetration type, they are unsymmetric and symmetric contact. In unsymmetric contact, whatever master you choose, it will check for the master, and it will check for the solver will check for the master and for the slave. For the master, it should be penetrating, and for the slave, it should get penetrated. Okay, and but for the symmetric contact, it will check both master and slave for penetration. For like, it will do the checks on both master and slave. So if you choose symmetric contact, it doesn't matter which one is master and which one is slave. So you can just go on and choose whatever surface you want, and the solver will do everything for you. So generally default option is symmetric contact, but yes, in our case we don't use it, and we are going for offset bonding. And my master surfaces will be the base faces of this plate. So this, and this, and my slave will be the beams attached to the base. Excuse me. So moving on, yeah, this one, all the one on the 4 sides, and then from the bottom. So the 4 sides are complete, and now from the bottom. So we have few on the bottom. This one, then this one. Okay. I think that's all.
Yeah,
Yeah,
looks good.
looks good. My maximum activation distance will be 20 mm. If you have any question about maximum activation distance, just let me know and I'll clear it out. Okay, so this is our model complete, and we are good to run our model and see what the results are. It shouldn't take long, but yeah. So that's the frame analysis part that we had. And
Yeah, I know, I appreciate that. We're almost to the hour.
Yeah.
We've covered quite a lot, okay? We hope to have a Q&A session afterwards, right? Now, I think the problem is, what we'll do is, as we're outside of time, right, what we can do is we'll reply back to your responses or any questions you may have. Please feel free to contact us both, okay? And what we can do, there is a few questions in, a few queries in. I think what's the best thing to do in order to save time on the call is I will take those questions offline,
yeah,
and we reply to the candidates if everybody's okay with that,
yeah,
with an explanation or a solution to the question you may have. It's just, obviously we're close to 11 o'clock, and again, there's questions in there, like, for example, why are you using shell elements versus mesh and solid, but we can get back to that and give you a good idea. I hope you found this informative. I hope it gave you a good taste of what Nastran's capabilities can do and do for your business going forward. There's a lot of functionality in here, and again, I think I feel myself we've only touched the tip of the iceberg here, really, with its capabilities. But as Julian's going to demonstrate, just to close out the call. Perfect, yeah.
So yeah, so you can see I'll show you the displacement part. That makes more sense rather than stress. So I'll show you how much deformation it has occurred and how it calculates everything. So you can see the beams and everything bended, and I showed you the cross-section input also. So if you want to include your cross-section of the beams into the analysis, you can do that, and that's the result from the analysis. That the frame, I don't think so. It's showing me 0.4632. So this is basically a very this representation is not a true representation of what's happening. I'll tell you 1 second.
So in a lot of cases, these results are exaggerated to kind of
Exactly.
give you a better feel of how the part would react.
So you can see over here the deformation scale. It is 10% more exaggerated of actually what is happening. So if I go to actual, you will see probably no deflection on the sheets and anything. So it's almost like original. So it's telling us that it can definitely withhold the load that we have applied, and this model could be good to go. So that's mostly about it, and I think we are good to.
Yeah, I think that, like, again, just to kind of close off the call, I do appreciate it. We did really hope to have a Q&A
Yeah.
session, but I understand that people's time and commitment as well. There's an hour taken out of your day already, so I'm conscious of that. So, look, I do appreciate it. Please, what we'll do in the chat box, we'll just put in our emails, okay? And we'll pass on our emails to our contact details to the attendees, okay? And please, we'll come back to, there's questions already on the list, so we can get back to those questions very quickly this afternoon. And we can take it from there if you have any further queries. We do plan to hold Nastran training in the future over the next 3 to 4 months. So we will have a Nastran day where we go through everything kind of Nastran and what's there and what's available to us. So without further ado, I'd like to thank you for your time. I think, Tarun, do you have anything to add to this? Or?
No, I'm good. I just want to tell Rinaldo, I'll get back to you. Like, I know where you are confused, so I'll probably go back to you in a personal email or something like that, and I'll discuss this thing with you personally. But thank you everyone for coming to this webinar, and it was great having you. I think we gave you a good understanding of what Nastran is and what the capabilities are, and I hope this makes a difference in your business or the product you are designing, gives you more insight and anything. And if you definitely need help, please contact ProCAD. They'll be happy to help.
That's great. We'll sign off with that. We'd like to say again, big thank you. And our next webinar series is in relation to CAM. But we will get back to you on this and kind of give you more further dates, more information on Nastran as it progresses for us. So with that further ado, thank you for your time. Enjoy the rest of your day, and we'll chat soon.
Thank you. Bye-bye.